This is the final lab of CS147. Here we will be developing the processor at the gate level. What we have discussed during this course. This is the final phase. So what you need to implement is a data path. First of all, it may be in the data path.v. The top level structures are all written in that in the file I provided you. You need to fill up the implementation part of it. You don't need to worry about this IO port listing and those part. Those things already have been taken care of. Well, if you open this file datapath.v, you will find a module definition with the port listing like a control port with a 32-bit clock reset, 32-bit data in, 32-bit data out, address, and 0. Essentially, like if you recall the data path, what it does, it basically reads some data in, instruction in, and depending on the instruction, it spit out some data for writing into the memory, data part of the memory, and it spit out the address of that memory to be written. And also from the data path, it actually needs to spit out the 0 flag, which is an exception. That 0 needs to be taken care by the controller of the processor. Now the data path, you can take this data path as it is. We discussed so many times on this data path and how this data path implement our target assembly language. So you can use these as a baseline, or if you feel you can use your own data path, that's also okay. Bottom line is that this data path should support the assembly language we were discussing, we're targeting throughout this course. So that is the main point. But you can take this as a solution. Okay, so couple of points to be noted in this data path. There is a separate data in and separate somewhere there would be some data out also. So basically okay, so this one is giving out the address of the memory where things need to be written out, and also this part is coming from the memory either for the instruction read or for the data read. So that's what it is going back as an data or as an instruction, if you look at that. And also there is a data out. This is mainly to write out the data into the memory. So these are all top level port. This is output port, this is input port, this is output port. And control signal, if you look at the previous slide, the control bus, this is a generic control bus, and what we need to do, we need to go and assign each bit to each of these control. That assignment is up to you. So one of the control index will be connected to the PC load, another will be the instruction register load, stack pointer load, this register file read write, those signals, all these control signals of the mark selection signals of the multiplexer will also be connected to one of the control bit in the top level control bus. So so that assignment you need to define, and depending on that assignment from the state machine, the controller control word will be spit out accordingly. So it's very unlikely that two of you will have the same control word to be issued from your control unit, because it's an individual choice of assignment of which control or selection signal goes to what control bit index. So that part is very unique from implementation to implementation. Now, as a control unit, so we'll not do a get level modeling of the control unit because that is too complex to do at this point. We'll stick to the behavioral model like our previous RTL or behavioral model control unit. We already know how to implement that. The difference is from the previous project to this one is that in previously we had only handful of control signal like control read write for the register file, read write for the memory, and one or two this and that, right? So we could afford to actually explicitly specify the control signal value on each of these. Now this gate level project has many more control signal, especially the selection of data in the multiplexer. That's why instead of issuing the individual control signal, we just write down a control word to be issued from the control unit, which is 32-bit, and that each cycle, each steps, instead of issuing individual control signal, we just write out the control word out of the control unit. And this control word will go into the data path, and each index, individual index, depending on your mapping of the control signal, will be connected to one of the control terminal inside the implementation of the data path. Now, another point, please note that the memory.v, I have created a memory wrapper. Initially, if you remember the previous project, a memory, the data in and out was a in-out port. So that same line, 32-bit line, is either in the read mode it was used as a as an output port, and for a write mode it was used as a read mode. Now I created a wrapper around it so that data out and data in being separated. So it is this data out is a pure output port and this is pure input port. Inside it, what I did is that instantiate that our memory which has a in-out port, and then separate that out with using a 32-bit register and a Z buffer, which means that if it is a write operation, depending on the control, the output of this buffer will become electrically isolated or high Z state. Okay, so let's say it is my data in, okay, and it is a write signal. It's a write signal. So that means this guy is 1 with this little decoding logic with inverter and AND gate. This is 1. So this data in will be